Indonesia is the world's largest producer of oil palm, managing a massive grid of plantations that accounts for nearly 56% of global consumption. The stability of this industry relies on the continuous production of fresh fruit bunches. However, this ecosystem is under constant pressure from wild rats, the primary mammalian pest targeting the crop. On an individual level, a single rat consumes between 6 and 14 grams of fruit flesh every day. But the damage extends far beyond what they eat. Rats carry loose fruit back to their nests, hoarding 30 to 40 times their daily intake. In mature plants, this activity creates an unmitigated yield loss of 5 to 10% of total production. For immature plants, the impact is catastrophic, with damage rates reaching up to 80%. This mortality occurs because rats specifically target and sever the central growing spots, or apical tissue, of the young shoots. When this point of growth is destroyed, the plant dies and must be replaced. Despite these universal risks, field data shows that neighboring plantation blocks with the same planting age and geography often experience vastly different levels of infestation. These discrepancies indicate that the carrying capacity of a plantation is not a fixed geographic certainty. Instead, it is a variable dictated by the microhabitat architecture within the block. To analyze this relationship, researchers conducted a survey across mature oil palm plantations in West and Central Sulawesi. The study area was divided into 30-hectare blocks to isolate environmental variables. Researchers established a trapping density of 20 traps per hectare, monitoring the results over 3 consecutive days. Because capturing every rat is impossible, they used the zip-in removal method, a statistical formula that estimates total population size based on the decline in catch rates over the 3-day period. To quantify the resulting impact, they employed this scoring system, which classifies the scale of damage on a scale of 0 to 4. A score of 4, or severe damage, is triggered when an attack affects more than 10% of the surveyed bunches. By combining the area of the attack with the severity of the score, researchers calculated the total intensity of damage. Standardizing these biological observations into mathematical metrics, comparing population estimates against damage intensity, allows for an objective assessment of why specific environments fail to contain the threat. This chart details the trapping results from both locations. The survey reveals that the infestation is dominated by 2 specific species. The primary species found is Rattus teomonicus, representing 67% of all captured rats. The secondary species is Rattus tonnesimi, making up 32%, which is typically a commensal pest found near human settlements. To understand why Rattus teomonicus is so uniquely successful in this agricultural environment, we have to look at its physical adaptations. In these specimens, look specifically at the length of the tail in relation to the head and body. Quantitatively, these rats have tails reaching up to 240 millimeters. This exceeds their combined head and body length, which averages around 202 millimeters. This elongated tail functions as a counterweight, providing the biomechanical balance necessary for high-altitude movement. This morphology defines Rattus teomonicus as a canopy rat, granting it climbing abilities that exceed those of other terrestrial rodents. It allows them to bypass ground-level obstacles entirely, utilizing the 3-dimensional structure of the palm trees as their primary habitat. Any pest management strategy that treats these animals as strictly ground-dwelling is ignoring their most significant biological advantage. The impact of environmental management becomes clear when we compare 2 blocks of the same age, Block OC12 and Block OH02. Block OC12 is well maintained, pruning is frequent, and the ground level is kept clear of dense scrub. This lack of ground cover restricts movement and eliminates potential nesting sites near the base of the trees. Consequently, OC12 maintains a very low population density of just 12 rats per hectare. This results in a manageable damage intensity of 4.9%. Contrast this with Block OH02, where environmental maintenance has been largely ignored. The primary variable here is dense weed growth, reaching heights of 60 to 100 centimeters. These weeds provide predator shielding. They make it nearly impossible for natural enemies, like owls, to see or hunt the rats from above. Furthermore, OH02 is located near unmanaged community plantations, which serve as a continuous source of new migrants. In this environment, the population density reaches 116 rats per hectare. This leads to a severe damage intensity of 15%. The lack of physical maintenance creates an ecological failure. By providing cover and structural complexity, the plantation artificially increases its own pest-carrying capacity by nearly 10 times. In these unmanaged blocks, the 15% damage intensity recorded involves losses that occur well before the fruit is harvested. This image shows how unpruned palm fronds physically touch one another, creating canopy bridges that allow rats to move from tree to tree without touching the ground. They use this structural complexity to build permanent nests entirely within the fronds, protected from predators. This arboreal lifestyle allows for a hidden secondary behavior. Stomach analysis reveals that 15% of the rat's diet consists of insects. To secure this protein, rats actively target and consume the male flowers of the oil palm. Their specific target is Eladobius cameronicus, the primary pollinating weevil of the tree. The rats feed on the eggs, larvae, and pupae living within the spikelets. By hunting these pollinators in the canopy, rats compound the yield loss. They degrade the current harvest while simultaneously reducing the fertilization of future fruit. By aggregating the data from every surveyed block, researchers shifted from individual observations to a predictive mathematical model. This linear regression plots rat population density against the resulting intensity of damage. The relationship is defined by the equation y equals 4.911 plus 0.091x. In a practical field setting, this means that for every single additional rat per hectare, the intensity of total crop damage increases by 0.091%. The strength of this relationship is demonstrated by the coefficient of determination. An R-squared value of 90.1% indicates that the population density of rats accounts for nearly all of the variance in observed crop destruction. This data indicates that traditional baiting, scattering chemicals on the ground, is an insufficient response to an arboreal pest. Effective control requires engineering the plantation environment to remove the rat's structural advantages. This necessitates two specific maintenance protocols: aggressive weed clearing to expose rats to predators, and strict pruning to eliminate the canopy bridges they use to navigate and nest. In the oil palm ecosystem, high yield loss is not an inevitable act of nature. It is the direct mathematical result of the microhabitat architecture.